Let's talk about log-log plots and semi-log plots. Sometimes the relationship between two variables is linear. For example, the relationship between household income and life expectancy is linear. Look at this. This is really close to a straight line for both the men here and for the women here. Let's interpret this. If you're a man and your household income puts you in the first percentile, you can expect to live on average to 72 years old. But if your income puts you in the 99th percentile, you can expect on average to live to 87 years old. 15 extra years of life on average for being wealthier. Kind of sad. So again, we say this is linear. These relationships are of the form y equals mx plus b. But sometimes we don't have y equals mx plus b, okay? Sometimes the relationship between two variables is some other power function, like y equals, okay, not x to the 1, but x to the 2, x squared, or x to the 3, x cubed, or x to the 1/2. In other words, square root x. So sometimes that's what the relationship looks like. Here's an example. We're going to look at the mass of a mammal and the basal metabolic rate, how much energy it burns. The relationship between these two is a power function of the form y equals mx to the n. It turns out it's y equals 0.6 x to the 0.7. That's what the relationship looks like. That's the function that best models the data. If you were to graph y equals 0.6 times x to the 0.7, here's what the graph looks like. Again, they're not all going to perfectly fit on this line, but this is the line. This is the line. It's not a line. This is the curve that best fits the data. Here we're measuring mass in grams, and we're measuring basal metabolic rate in milliliters of oxygen per hour, burned per hour. This is for mammals. Okay, now usually in graphs, the tick marks are on the x-axis and the y-axis are at 1, 2, 3. It's exactly what we have here. In a log-log plot, the tick marks on the x-axis and the y-axis are at 1, 10, 100, 1,000, etc. Why? Why would you do something weird like that? Well, suppose the relationship between x and y is y equals mx to the n, just like we saw a moment ago in the basal metabolic rate. If we use a log-log plot, then the dots will form a straight line instead of a curve. Here's what it looks like when we use a log-log plot. So again, notice the numbers on the axes are powers of 10, 1, 10, 100, 1,000, etc. And these data do seem to fit a straight line pretty well. So again, rather than have a curve like this, if you can express it logarithmically, you end up with a graph that looks like this. So again, if you use logarithmic scales, if you use a log-log plot, then the data are more likely to follow. They'll follow a straight line. Sometimes the relationship between two variables is not a power function. Instead, it's exponential. In other words, it's of the form y equals a times b to the x. In that case, here's an example. This is the estimated risk of Down syndrome according to maternal age. So there's a strong relationship between the two, and it's exponential. The older the mom, the more likely the child is to have Down syndrome. And it's exponential. It's not a linear. It's not a line. It's exponential. So in other words, this relationship is of the form y equals ab to the x. When the relationship between two variables is exponential, in other words, this is of the form y equals a times b to the x, then we use a semi-log plot. The tick marks on the x-axis are at 1, 2, 3, etc. And the tick marks on the y-axis would be 1, 10, 100, 1,000, etc. And why do we do that? Then the dots will form a straight line instead of a curve. So if you just use linear, you end up with something like this. But if we were to use a logarithmic scale, on the y-axis, it would look different. It would follow a straight line. Okay, when the relationship between two variables is logarithmic, in other words, it's of the form y equals a plus b log x, then we use the other kind of semi-log plot. The tick marks on the x-axis are at 1, 10, 100, 1,000, etc. And the tick marks on the y-axis are at 1, 2, 3, etc. And why do we do that? Well, as you might expect, then the dots will follow a straight line instead of a curve. So notice, in this case, it's the tick marks on the x-axis that are 1, 10, 100. In the other case we saw, it was the tick marks on the y-axis. Okay, we can express not just scatter diagrams. We can also express skewed histograms by re-expressing them using logarithmic scales. Here's an example. This is the annual salary in millions of dollars for CEOs in the Fortune 500. This is several years back. So this is a really, really skewed distribution. This one person here who's making $156 million. Very skewed. When you have a very skewed histogram like this, sometimes it's better, so that you can get a handle on the data, to re-express it by taking logs. So if you, instead of taking the compensation, you took the log of the compensation, this is what you'd end up with. To be honest, this is a little confusing. I would rather they put 10, 100, 1,000 instead of writing log compensation on the bottom. But just a warning, it is what it is.